The resistance of a light bulb indeed changes with temperature. A cold light bulb at room temperature exhibits a much lower resistance than a light bulb that is hot and actively producing light. This phenomenon is due to the filament material, typically tungsten, possessing a positive temperature coefficient of resistance, abbreviated PTC. This means that as the temperature of the filament increases, its resistance also increases. When the light bulb is initially switched on, the filament is relatively cold. Consequently, the resistance is low, resulting in a surge of current. As the current flows through the filament, it heats up rapidly. As the filament's temperature rises, so does its resistance. This increasing resistance then limits the current flow, eventually stabilizing at a lower level than the initial surge. This is why a light bulb might briefly shine brighter immediately after being turned on before settling into its normal brightness. The formula E equals I times R, or volts equals amps times ohms, is valid for calculating resistance, but it's crucial to use the correct voltage and current values that correspond to the filament's operating temperature. When the filament is cold, its resistance is low. For example, if a 60-watt light bulb measures 16 ohms when cold, this measurement is accurate for that specific temperature. However, when the bulb is operating at its design brightness, the filament is much hotter and its resistance is significantly higher. To calculate the resistance of the hot filament, you can use the power formula P equals E times I, or watts equals volts times amps, to determine the current draw. Rearranging the formula, you get I equals P divided by E, or amps equals watts divided by volts. For a 60-watt light bulb on a 120-volt circuit, the current is 60 watts divided by 120 volts, which equals 0.5 amps. Now, using Ohm's law, E equals I times R, or volts equals amps times ohms, you can calculate the hot resistance R equals E divided by I, or ohms equals volts divided by amps. Plugging in the values, R equals 120 volts divided by 0.5 amps, which equals 240 ohms. Therefore, the resistance of the 60-watt light bulb when hot is approximately 240 ohms, while its cold resistance is much lower, around 16 ohms. The difference in resistance between the cold and hot states is substantial due to the PTC characteristic of the filament material. The relationship between resistance and temperature is not always linear. The resistance of a conductor at a given temperature can be calculated using the formula R sub T equals R sub 0 times 1 plus alpha times the quantity T minus T sub 0, where R sub T is the resistance at temperature T, R sub 0 is the resistance at a reference temperature T sub 0, and alpha is the temperature coefficient of resistance. The temperature coefficient of resistance, alpha, is a material property that indicates how much the resistance changes per degree Celsius, or per degree Kelvin. For tungsten, the temperature coefficient of resistance is positive, typically around 0.45 per degree Celsius. This means that for every degree Celsius increase in temperature, the resistance increases by 0.45 times the resistance at the reference temperature. Using this formula, you can estimate the resistance of the filament at different temperatures if you know the resistance at a reference temperature and the temperature coefficient of resistance. For example, if you know the resistance of the tungsten filament at room temperature, say 20 degrees Celsius, and you know its temperature coefficient of resistance, you can estimate the resistance at its operating temperature when the bulb is lit, which might be around 2500 degrees Celsius. The resistance of the filament at 2500 degrees Celsius would be significantly higher than its resistance at 20 degrees Celsius due to the large temperature difference and the positive temperature coefficient of resistance. Furthermore, the power dissipated by a resistor, such as the light bulb filament, is given by P equals I squared times R, or watts equals amps squared times ohms. Since the power is constant for a given light bulb rating, say 60 watts, as the resistance increases with temperature, the current must decrease to maintain the same power output. This is another reason why the current through the light bulb is higher when it is first turned on, when the resistance is low, and then decreases as the filament heats up and the resistance increases. The resistance of a light bulb filament is also affected by other factors, such as the material of the filament, the dimensions of the filament, and the presence of any impurities in the filament. Tungsten is the most common material used for light bulb filaments because it has a high melting point and a relatively high temperature coefficient of resistance. The dimensions of the filament, such as its length and diameter, also affect its resistance. A longer and thinner filament will have a higher resistance than a shorter and thicker filament. Impurities in the filament can also affect its resistance. Even small amounts of impurities can significantly change the resistance of the filament. In summary, the resistance of a light bulb changes with temperature due to the positive temperature coefficient of resistance of the filament material. The resistance is lower when the bulb is cold and higher when the bulb is hot. This change in resistance affects the current through the bulb and its power output. The formula E equals I times R, or volts equals amps times ohms, can be used to calculate the resistance of the filament at different temperatures if the correct voltage and current values are used. The temperature coefficient of resistance can be used to estimate the resistance at different temperatures. And finally, the power dissipated by the filament is given by P equals I squared times R, or watts equals amps squared times ohms, which relates the power, current, and resistance of the filament.